so let's start right in. A little TOC, of course, is I will talk a little bit what is asynchronous code again for all the people in here who are not so familiar with Boost ASIO and with asynchronous code, of course. And then I will come to the coroutines, and then you can awake the advanced programmers who then want to listen right back in. Yeah, so as you might know, life is a series of events. Like if a human clicks on the mouse, it actually translates to an interrupt, and in the end, we have an event in our program. It's the same for network programming. Usually you're waiting to actually to receive something, or you're even waiting that you have sent your packet on the line and you have a serialization time. And so, yeah, usually, especially with input and output, it's still a series of events. And especially also if you're dealing with user interaction and also with timing, for example. So if you ever programmed bare metal, you're already familiar with interrupts. It pretty much drives the whole world for yeah, any moment-driven programming. So how can we do this? The first pattern usually beginners do is, of course, we are polling things. So we're asking, are we there yet? Are we there yet? Are we there yet? And usually you get no, no, no. And you still keep asking. And of course, the problem is, for example, if you're programming in a freestanding environment, if you're programming bare metal, that really doesn't help, because then your CPU is only really doing one thing. You can only listen, for example, has the voltage changed on this one pin, and then you can only check the one pin. So of course, CPUs, since ever, have in hardware support for this, and these are the interrupts. Usually interrupts are just triggered by a voltage change, for example. And so you see, okay, the busy wait is really not what you want to do, but it's what the first thing which comes to mind for a beginner, of course. Then we are getting to a blocking API, which means this is also what we could call synchronous programming. Like if you ever programmed a game with SDL, you would call the poll event function, and this function would block until the next event has happened, like the user clicked something, or your timer elapsed, or there's something new from network. And this is basically what also many people are doing. But of course, as it's synchronous, your thread is still blocking and you can't do anything else in the thread at least. Of course, for example, with this thread, sleep for 5 seconds, you're misusing the operating system scheduler as a timer, for example. So next we have what is pretty common, pretty popular in the Java world, in the Qt or Qt world, in the JavaScript world. You have one event loop with usually exactly one thread, and this thread is usually also a special thread. And this event loop then dispatches to callbacks when something has clicked. In the Qt world, we call this signals and slots. And in the JavaScript world, of course, this is when all the jQuery callbacks are called, for example, via the browser. And yeah, and usually, why is this also pretty common in JavaScript world or even the Python world? Because of this one thread design, you don't have to care about data races, about have to synchronize on things because it's concurrent code. If it's only one thread, you don't have to synchronize because it's still executed only by one in order. So you are spared a lot of pain, and also usually these languages are also garbage collected. Of course, Qt is not really garbage collected, but as I say, Qt is Java in C++ form, so you have some lifetime semantics, of course. Also, if you got the question, what has concurrency to do with asynchronous coding? You can use asynchronous pattern to do concurrent programming easier. Now I will also show this. It's a proactor pattern, so you can, for example, use Boost ASIO, which is the library I will show to you how to combine with coroutines to also program concurrent multi-threaded code in a much more readable sense, I would say, at least now with coroutines. So the difference between concurrent asynchronous code is just you don't have one worker thread which is churning this one function. You can spawn as many worker threads as you like. This is pretty much the only difference. And in Boost ASIO, this is the run method of the I/O context. This is where you actually turn the handle to let your callbacks execute. And of course, this is optional, so you can also use Boost ASIO in only one thread. You can even tell Boost ASIO there's only one worker thread, so that Boost ASIO can do some optimizations and will not compile with mutexes and stuff, so that the Boost ASIO data structures are not anymore protected by mutexes. And to put simply, for all those who ever had heard a computer science lecture, you can also put it into terms that it's actually userland scheduling, userland cooperative multitasking. Because of course, because you don't have an interrupt setup which can execute and do a preemptive strike on a callback, it's still cooperative multitasking and not preemptive multitasking. That's pretty much the only difference in operating system theory. And the nice thing is Boost can also use the operating system native facilities, so that in the best case, it might be even transitively directly from the network card interrupt over the kernel directly in the userland code. So it should have some minor technical difficulties there. Yeah, so you get in this, as I said, the callback hell. If you ever looked into the CPPCon talks about how do we do, for example, an HTTP server with Boost ASIO, you will find a pretty much common pattern to use shared from this and the STD shared pointer to get rid of your lifetime problems in C++. So use retain counting, and then you will always from one callback to the next, because you're only setting up the callback and your lifetime would end, your scope would end, of course. Because if I'm saying for a timer, please elapse in 5 seconds, and here's a callback for that, then of course this function will end because it said, okay, call me in 5 seconds, and everything will go out of scope. And everything would be deallocated, the deconstructors would run. So how do we do this? Of course, we're putting everything in a shared pointer, and we are throwing the shared pointer into the lambda, into the callback, so that this is stored in the callback, and then when the callbacks actually execute, 5 seconds later, we still have our lifetime, we still have our scope, we still have our variables. And the problem is you have to do this every time. Always you have to think about, okay, STD shared from this in the capture list. You can even forget this, for example, and then funny things happens, of course, because then your shared pointer will reach 0 and we deallocate. If, for example, if you just put in the capture list at this pointer and not the shared from this pointer, then you're basically in undefined behavior, because then the lambda will execute while the shared pointer was already deallocated. And yeah, so this is not very readable code. And don't be alarmed, of course, you will find all this code I'm showing you, except for the one sometimes in the slides, but you will also find the slides in the GitHub repository, where you also find a QR code at the end. And so how do we get this code a little bit more readable and nicer? If you look in the JavaScript world, JavaScript had made, because it was very early in the productive use of asynchronous code, because it was running in the browser and had to deal with these issues basically since the start of the 2010s. It was coming from the callback hell. It then was using promises. Of course, the promise in future world between JavaScript and C++ is not really comparable because in C++, you don't have this executor, this one thread pattern which I showed before. So you can't chain these promises via then, because in the C++ world, then the question would arise, yeah, who is executing then? Which thread? You didn't say which thread, because you're free to use whichever thread, whichever concurrent regime you want. While in Python and JavaScript world is this one magic thread, don't worry about it. And then it even involved more to coroutines. And now you can just write your callback code, again, asynchronous code, and via compiler support, it looks like usual synchronous code, but in coroutines, the compiler can suspend the execution of a function. It's not a regular function anymore, but the compiler will suspend this function, will put everything of the scope in this function in some magic box, and when the timer elapses, for example, or there's some new data on the network line, then the compiler will take this function back out again and will resume execution at the one point where it was resumed. And for this, we also have 3 new keywords in C++. But if you want to use it actually, and you go to cppreference.com, for example, it gets a little bit weird. And this was my personal experience when I actually was about to introduce coroutines at my employer. And yeah, it was quite a fun. And some links I also shared to you at the end were actually helping to get coroutines usable and how to, basically which ends of Boost ASIO also fits in which part. Because the C++ community, of course, it's again the same problem or the same liberty to use C++ in very different environments. Maybe you're running bare metal, you don't have an operating system, but you still want to use coroutines. Maybe you still want to program asynchronous. And so the C++ committee had to give you a lot of opportunities and let many things blank. So coroutines are not directly usable out of the box. But there's the place where Boost ASIO comes in, because thanks to Boost ASIO, they have already implemented what the C++ standard would expect you to implement otherwise. And the basic gist of it is that a lot of the magic will be in the return object of the function, or not function anymore, now it's a coroutine. This is a quote from the C++ 20 standard, or because you don't want to pay the 130 Schweizer Franken, it's usually, we all use the C++ draft, of course. And the important thing is, a function is a coroutine if one of those 3 words are in its body. It doesn't matter if it's ever executed, it can be in an if-false statement, for example. Oh, yeah. The important thing is, if one of those 3 keywords at least is in there once, it is a coroutine. Remember this because some actual learnings of productive use of coroutines have shown a little bit of some surprises, I would say. Even for the C++ veteran, I would say. And this short story is you want to use Boost ASIO co-spawn to actually start a thread of execution in a coroutine, and you want to use the Boost ASIO awaitable as the return type of this function. And in this return type, actually a lot of the execution behavior is stored, and also the lifetime, the objects in the scope of the coroutine will be stored in there. So here you see the old way of doing things in Boost ASIO with callbacks again. Like we have a timer, and we want this timer will elapse after 5 milliseconds. So of course we give this timer a callback, and yeah, in this callback we call another callback because we want to do something else after that. And yeah, that's the old way. So a lot of lambdas, and all the problems are even left out. And also because you might want to cancel the timer, for example, then Boost ASIO also expects that your lambda will then have a parameter set up where you can check if any error was why this timer was elapsing, like for example, because someone canceled this timer prematurely. Usually if you program ASIO, you want to do this because someone said, okay, please terminate this service. The user pressed Control-C, for example, you have the SIG term signal, your process shall end, then usually you want to cancel all your timers so that you can speed up the termination process. And so with coroutines, this now looks like this. It's just one function, and we are using co-await. And the important thing is, wherever you see the keyword co-await, this function will suspend its execution and resume the execution after the timer has elapsed. And co-return is also the same for then returning your value, because you can see the actual return value of the coroutine is the template parameter of Boost ASIO readable, the return type. So, of course, to return an integer, we use co-return. But yeah, this is basically, and if I will also show a live demonstration and also a little bit more realistic code or some scenarios where you can even say, see how much this really helps. But of course, this is now tailored for the asynchronous I/O-driven design. You can, of course, can also use coroutines for more scientific computing. Then it's basically because you're using coroutines as a generator function, and then you would use more the keyword co-yield. But because this would prolong this talk even further, and it wasn't really a use case for me, I will show you basically centered on asynchronous code. And so this is actually a visualization I made to help you understand. You can see again what I already said. If you're hitting co-await, for example, this function will be suspended. And you have still think if you can run this concurrently, so that one of your worker threads, which are turning the handle on the event loop, as I said before, but then execute when this coroutines resume. This doesn't have to be the same thread, even. Of course, usually in Boost ASIO, if you do concurrent stuff, usually you want that maybe you have to synchronize. You would need some kind of mutex. And for this, Boost ASIO has the so-called strands, which is an object which you would execute on, which then again introduces the guarantees that only one callback is running on this strand and in the same order as the callbacks have been scheduled. So whenever you hear strand, you can hear mutex, but the important thing is, after the co-await, or during the co-await, during the time where the coroutine is suspended, the strand will also be released. And this is important because why have I written get iterator and use iterator in there for an example? The problem could be that another coroutine would modify a shared container, for example, like SED vector or SED double-ended queue, for example. And the problem is, before the co-await, you would get iterators from this container. You would co-await because you wanted somebody stores something in there, or just because of some other reasons. And then after you resume, these iterators, of course, could be invalidated. Because if you shared this container with someone, even though you synchronize on this strand, you have to keep in mind that this code executed and maybe modified the container. This was basically a real-world bug we already had with the coroutines, so it's actually one of the in-field learnings after using coroutines in productive usage. And yeah, so now I can show you some actually live code, which maybe makes it a little bit easier to see and to understand if you can see, and also some of the surprises you might even not believe. Like, this is the new way of doing stuff. So this is our main function. Here you can see in line 42, this is where we turn the handle. This is where we turn the event loop. And it's even the main thread which is doing this. And here we have, this is, for example, this could be a Boost ASIO TCP acceptor, which is usually if you have a server running, then you have an acceptor running, and every time a new TCP client connects to the TCP server, then the acceptor would unblock and have a new endpoint. And basically, a very common and usable pattern for this is then you would just program your own session object, for example, or your own connection object, and you would just still use shared from this and would say, okay, here's your endpoint, here's your new client, here's your own shared pointer, and be happy and run as long as the connection, as long as the client is doing stuff with you, and you have your own strand, you have your own shared pointer, and if the client at some point says, okay, we can terminate this TCP connection, here's the fin signal, then you would basically just stop processing in this own connection object and would just let the shared pointer go out of scope, and you would clean up yourself. So you see this in start loop, where we use Boost ASIO correspond. This is where we are going into the coroutine world. So this function would finish, and this would be scheduled for execution. And then in run, the actual coroutine would run. In this case, this is loop. And the nice thing is to keep ourselves allocated to not run out of scope. The only thing we have to do as a coroutine is to accept ourselves as a parameter, as the shared pointer ourselves, and we would clean up ourselves in line 23 when we ever get out of scope. And of course, this while true loop could be, for example, an atomic. If you say let's terminate the server, or if we, for example, see that the connection has been terminated by the client, or some session ending signal, whatever you want, and then we would know, okay, we can just go out of our loop, go out of scope, and that's it for cleaning our TCP connection, for example. And the nice thing, of course, about Boost ASIO is whenever you see a timer, you can use the same for TCP or UDP connection. To send something in a buffer or to receive something, you can co-await on a TCP or a UDP connection, and you can co-await on sending something on the line. That's the nice thing about it. And yeah, if you actually, of course, run this, then you would see, oh, that's the old way, sorry. This is the wrong target. As you can see, this will wait for 1 second. We'll co-wait on this timer. We'll call op-A. Op-A is just printing out op-A with also incrementing the session data, which is just an example for scope issues, or for an example that there are no scope issues. And yeah, and then we will call op-B, and this will happen until either we would say, yeah, while this loop is true. And also the nice thing is you don't have to use all those boost errors anymore, because now also exception handling is working again as in the way we were used to, and not via a boost error code given into the callback. Because this was the old way, you could see we would start the loop, and we would just start, our loop is not written explicitly anymore, but we now have, in the old way, we would have a callback here, because we would have the first callback, which calls then the other callback, and then this callback would call the callback for its timer, and when this timer elapsed, it would set up the timer again with another callback, which will call itself again, and this is the old way of writing asynchronous code. And as I can see in your faces, this is not really a nice native way to program. So this is where the coroutines were helping out so much. And now to also come to the learnings about the surprises. As I said, let's start with the, where is it? Damn it, I thought I have written it, but that's no issue. The funny thing is, if you look in this code at line 27 and 28, you are seeing that we seem to call this function blocking and blocking too, right? So you might wonder yourself, shouldn't it execute these functions directly in line 22 and 28? Who thinks this would happen? Maybe raise your arm and be honest. Who would think that that's the basic behavior of the call operator, and in the C++ standards is if there's a call operator, it would call the function, right? That's the funny thing about what I said, that coroutines are a subset of functions, and all functions which have the keyword into it are not regular functions anymore. And the call operator is not behaving the same for coroutines as for functions. So if I'm executing this with the debugger, and this is the target UB lurking, oh yeah. And I can also put a breakpoint there and a breakpoint there, so you can see I'm not cheating. So we go here. Oh. Seem I have step over, and you see no execution of the breakpoints. If I just say, okay, resume program, oh, now we're in the breakpoint. But if you look into the call stack, you will see we are running here, where we are turning the event handle. And this is, you can see, this is all the code you need if you want to also use concurrent code for Boost ASIO. I'm just spawning some threads, and all those threads can turn the handle concurrently of the event loop. So this is even concurrent code already, but this is just something else to show. And if you also see this Boost ASIO detached says just, okay, I don't want to be informed when the coroutine finishes, just let it run, and the main thread will just not go out of, will just not exit because it's joining these threads. So the main thread is not even executing anymore the callbacks, but what you sometimes want, a worker thread is doing this. And yeah, so basically now, okay, we know that the call operator has changed its behavior, but there's some very bad thing also in there, and I already hinted it with the comment. If I accidentally delete this keyword, the behavior will change. Because now, for some point, of course, it should not even compile, I guess. oh no, it compiles, but it's undefined behavior. Because, okay, I want to step over. Oh, it's calling it directly, just because I have erased the keyword. Because now for the compiler, this is a regular function and not a coroutine anymore. This is now even undefined behavior, because if you look closely, now this is a function which returns non-void. It returns actually Boost ASIO awaitable void, which is not equal to void. And now you're running into the undefined behavior of a non-void function without a return statement. So now you have undefined behavior because the return statement is missing. And yeah. And this is not a coroutine anymore. The funny thing is, it will be a coroutine again, and we will have well-defined behavior again, even if I write this. Oh, fine. Now everything is peachy again. Because now, even though this the keyword can never be reached, it's unreachable code, this is a coroutine again. And we also in well-defined behavior, because coroutines are allowed to not return anything when they are void. Yeah, that's some feature they added to coroutines, but only if it's actually a coroutine. Yeah, you could imagine how many pages of standard, and even though it was not really written well in cppreference.com, I also made an edit in cppreference.com to make it more clear, and then some other contributors are even stepping in, and we changed the whole article a lot more to make it more clear how coroutines behave. So now it also is written well in cppreference.com. If you might want to use the old way of error handling, for example, and you don't want to use exceptions, you can still more or less do this by modifying the so-called completion handler. And as for the steady typer, for example, you can just say Boost ASIO as tuple and also as awaitable, which says, okay, don't throw an exception if something bad happened, but please just return this for me so I can then do stuff with the error code. And another nice thing of completion handlers, you can even, if you have to wait until the coroutine finishes, you can use a future. And excuse me, it's just done by using, where have I written it? It should be, yeah, here, future get. Yeah, and it's just by using use future in co-spawn. So it's not detached anymore, it's use future. So line 27 will unblock after the coroutine has finished. Because the coroutine, if you look into it, is setting up a timer which will elapse after 5 seconds. And so only after we reach line 10, the future in line 27 will unblock. So it could come in pretty handy if you have some legacy code which is depending on blocking semantics via future, so you can use this way on adapting coroutine code into legacy code. You can see it's waiting for future, 5 seconds elapsed, it's done waiting. Yeah, and this basically pretty much concludes the whole talk, more or less. And just to recapitulate what we have learned, best ways to always include a co-return at the end of your function, so that you can't accidentally, for example, delete the last co-await statement, and by accident you have turned your coroutine into a function. And yeah, the call operator has changed its behavior in some cases. execution is suspended in a await. Always keep this in mind, especially if you have to synchronize using strands, for example. And most of the magic happens in the return value of the function in the Boost ASIO awaitable with its template parameter. And the funny thing is, this whole behavior, there has to be a keyword in the function. How do the other languages do this? The other languages here, you can see Python and JavaScript, they are just using the async keyword to put this in the syntax of the function declaration. So I guess for some reason the C++ committee were thinking, okay, we already have async as a keyword, I guess. I'm not sure. But for some reason they were thinking, yeah, we don't need this keyword, it's still a function, but with some magic if these keywords are in the body of the function. So it might be even an idea of look how much work it is to maybe even propose this to the C++ committee to still in the later versions to introduce the async keyword to also declare a coroutine in a more safe way, I guess. But yeah, it's a change, and of course, as C++ programmers, I guess we are used to that dangers lurk in every corner, but yeah. And these are also the links which help me to actually understand what is happening, and also basically on Stack Overflow, there's basically just one guy who usually there's just a dialogue with him because I ask a question and then it's usually always the same person who is answering me, called Sehe. Really nice contributor to Stack Overflow. Also thanks, shout out to him. And yeah, these are the links which you can also find in the GitHub repository. These are the Stack Overflow links I talked about, where I have asked those questions, where you can actually see where I was tackling these issues. And yeah, you could, as I said, you can still find everything there under this link and QR code. So I guess now we come to the interesting part, questions. I can also, of course, show you things live on the MacBook, where I had to use Conan 1 to actually get a newer Boost library, but yeah.
Or I actually two. The first is, what happens, or how do you detect whether you not awaited a coroutine? Which means if you call it, then not use co-await to await it.
Yeah, usually if you don't have to co-await in your coroutine. If I'm going back to the code, if you don't co-await for something, it will just execute. Of course, you still have to put a co-return in there to tell the compiler that's a coroutine. But if you don't have to wait for something, then you can just execute it as a normal function. Like, for example, new way.
Detect that you made this mistake in your code, not awaiting the coroutine, because then actually nothing will happen and your code will not run. And if you have a bigger code base, how do you detect that such an error?
I'm not sure if I'm understanding right.
Maybe you can just remove one co-await keyword maybe online.
Yeah, let me just use this example. So this is our coroutine, yes. Don't want this anymore. So, and for example, I will put an std cout in here, doing stuff. Wrong target. Yeah, it's just executing. Yeah, then the compiler would just for example, in this this is completion handlers. Now it's the compiling. Oh, I'm forgetting co-await. No, just some warnings. Yeah, it's then warning you that you're ignoring the return value of async await. But yeah, there's no. Maybe if of course we still need. It's not a coroutine anymore, but this shouldn't change anything. Yeah, you will get a warning usually because then you have this attribute called, how is it called? No discard.
Who makes sure that your coroutine isn't actually executed twice by the threads if you have multiple threads cranking the event loop?
Boost ASIO, because how often it's running concurrently is depends on co-spawn, because in co-spawn you start the execution of the coroutine, or you're not starting it even directly, you are scheduling it in the Boost ASIO event queue. And with a strand, one has to, I might add that there are two kind of strands in Boost ASIO. There are the old strands, which you can't use for coroutines, but you have the newer ones, which you then can, which makes it even easier. I guess it was just the code which I erased. Yeah, here you can see to synchronize the execution on a strand, you just give the strand instead of the I/O context to coroutine to co-spawn, because it's the same interface. They are both executors in the template world, and then blocking will run in the strands, and so I can even run it again or concurrently by just duplicating these lines. But thanks to strand, it will not run concurrently on the strand. It would not run concurrently because it synchronizes via the strand. But as I said, if you have a co-await here, be aware that when it's suspended on the co-await, then it can run, the underthread can run it also, because the strand is released meanwhile. You're welcome. Other questions?
The order of the coroutines, or the order the coroutines are invoked, is the same order as you spawn them?
Yeah, it's the same as I spawned them, or should be. Of course, if you have multiple threads, like in this code here, which are turning the event handle, if you're not synchronizing on a strand, then Boost ASIO has relaxed guarantees that it will run in the same order as it was scheduled. But these are where strands come in. If you are scheduling on a strand, like we do this here, then the strand guarantees that it, as you ask, then it will guarantee that it will execute in the order as it was scheduled. But you have to use this strand, this Boost ASIO strand.
Newway.cpp again. Newway.cpp, the other file. A and B being called alternatively. But am I right that you have a single coroutine in this case? There are not two coroutines who are called alternatively?
It's running because only one in serial, because we only call co-spawn once.
Example of a single coroutine, not two coroutines waiting on each other or being.
Yeah, because we only have one flow of execution here, I don't have to use a strand even, because we only scheduling this in the way which we are also executing. If I would have two co-spawns of loop myself, then I would have to use a strand. I would put this here in the private part, just below in session data, for example, and then I would just put the strand in here, and then everything, all would be PG again, although of course we would have two states of the loop, of course. But we won't have any databases.
Okay.
Question answer, I can, even if you have the time, I can put this into it.
So two coroutines or a single coroutine who...
So the intention was to show that you don't have this callback hell anymore. Because, for example, if this would be actual production networked code, for example, usually you would, for example, receive something from the TCP client, have some side effects, which may take some time, or which even is triggered by a timer. For example, in multimedia programming, you would have a timer which would put out the next video streaming frames in a timely fashion, and then you would even listen to receive something if maybe the client has to say something, for example, and then you would just begin again in the loop, for example. And usually then you would have a Boolean or atomic bool, for example, so you can terminate the server if you want to shut down the server in a graceful manner, for example. And if the TCP client don't want to listen anymore, then you would just, if you use Boost ASIO receive, for example, would get an exception, or you can use, as I showed with as tuple, you would get an error code, and then you would see, okay, the TCP connection was closed. I will just go out of the while loop and I will clean up myself.
Last argument in co-spawn, the detached. What are the alternatives, for example?
Yeah, as I showed, I guess it was here. Yeah, use future. Here you see another way. With use detached, this code will just execute. So as here, so this was new way, exactly. So we put a breakpoint in here to even show this via debugger. And with detach, and I will also put one in the loop. And as you can see, when I step over, okay, it's not starting to execute anything. And yeah, it's like a detached thread. It will just execute, and only the main thread wouldn't turn the context itself. Then it would go out of scope, and we have to put something to synchronize the main thread so it wouldn't go out of scope. And usually you sometimes want to wait for a coroutine, and this is why I have this code here. You can also say co-spawn, okay, use future, then you would get a future out of it. And then you can just wait on those future via get, and then you would synchronize on the execution of the coroutine. There might be even a third, but it was, I guess, for as tuple again. But yeah, these are the two major ones, I would say. Some other questions?
I noticed in the includes that there is an experimental in the path of one of the includes of the Boost ASIO. Can you say something about the state of these ASIO features with the coroutines? Is that experimental or is that not experimental?
It's not experimental. Basically an artifact when I copied code from one of my Stack Overflow questions in a Hassel, and yeah, and there was used for some other Boost ASIO versions. Of course, then you would have to use it because you have to use a more or less recent Boost ASIO. I guess at least Boost ASIO 1.8 should be fine. I'm using here 1.82. But as you can see, with 1.82, it's not experimental anymore. It's considered production grade in Boost terms, and of course also for the compiler.
Okay, thank you.
You're welcome. Okay. Then I would say, you know where you can find the code, of course, and thanks for listening. We are done.